So, hello everyone again. This is lecture 2 part 3 of ray optics and optical instruments. Today we will go on with the further discussions of total internal reflection. So, I am Sameer Lavankar. Let us begin our discussion. Okay, so course outline for you. We started with the introduction concept in which we understood the concept of ray optics, that first of all light travels in a straight line, and second is that the speed of light is equal to 3 into 10 to the power 8 meter per second. In reflection of light by spherical mirrors, we understood the concept of mirror equation, that is 1 by V plus 1 by U is equal to 1 by F. Before the mirror equation, we also understood the concepts, basic definitions, what is pole of the mirror, what is focus of the mirror, what is principal axis, and so on. In the last lecture, we started with the refraction concept, in which we understood the concept of Snell's law of refraction. So, basically the two laws of refraction. What is refraction? The phenomena which we observe this in real life. The first was the lateral shift, in which we understand that if a glass slab is being occurring in the middle of a incidence of a light from an air medium, then after the air medium has been attained again, there is a lateral shift happening in this portion. So, it is happening because of refraction of light, phenomena of refraction of light only. The second concept, that was the apparent depth. So, basically the apparent depth is nothing but the total depth divided by the refractive index. Next concept which we understood is this fourth concept, that is total internal reflection. So, right now we are on this topic, that what is total internal reflection. Okay, so let us move on to total internal reflection now. So, when the light travels from an optically denser medium to an optically rarer medium, at the interface it is partly reflected into the same medium and partly refracted to the second medium. So, this was been understood in the previous lecture only. This reflection is called as internal reflection. Now, when a ray of light enters from a denser medium to a rarer medium, it bends away from the normal, quite evident. So, as you can see that this was the original passage of light, but it bends away from the normal. Okay. Next is that, for example, the ray A01B in the figure, as you can see ray A01B in the figure. Next is that the incident ray A01 is partly reflected O1C. So, as you can see that O1C, that this is partly reflected and a part of it is partly and partly is refracted. So, so as you can see that the incident ray A01 is partly reflected and partially transmitted or refracted. The angle of refraction R being larger than the angle of incidence. So, this value of R is always this value is always greater than angle of incidence. Okay. Next is that as the angle of incidence increases, so does the angle of refraction, quite evident. As the angle of incidence increases, the angle of refraction is also keep on increasing, because you need to be at least, the angle of refraction has to be at least some value which is greater than angle of incidence. Why? Because it is always bending away from the normal. Okay. So, as the angle of incidence increases, so does the angle of refraction till for the ray A03. So, as you can see for A03, what is happening is that there is no for angle A, sorry, the angle of refraction is pi by 2 now. So, as you can see the angle of refraction is pi by 2 now. So, it is keep on increasing and we are pausing at a point at which the angle of refraction is 90 degrees. The refracted ray is bent so much away from the normal that it grazes the surface at the interface between the two media. So, as you can see, it is grazing the surface as in it is very near to the surface. This is shown by the ray AO3D. So, as you can see AO3D. Okay, so this thing has been explained. Let us move on. So, if the angle of incidence is increased still further, so that is that we are trying to increase this angle, refraction is not possible. As you can see beyond this portion there is no refraction possible. Why there is no refraction possible? Because angle IC was that point at which 90 degree was obtained, because then anything which will be greater than 90 degree will be always passing in the same medium only, it will not refract, because for the angle of refraction or refraction to occur, the angle of refraction should be in between 0 to 90 degrees. So, if the angle of incidence is increased till further, that is for example the ray AO4. So, this is the ray AO4 for you. Refraction is not possible and the incident ray is totally reflected. As you can see, the incident ray is totally reflected. Okay. This is called as total internal reflection. Okay, fine. So, this thing has been explained. Next is when light gets reflected by a surface, normally some fraction of it gets transmitted, quite evident. So, as you can see, when the light gets reflected by a surface, normally some fraction of it gets transmitted, as you can see in this portion here. The reflected ray therefore is always less intense than the incident ray, howsoever smooth the reflecting surface may be. So, however smooth the reflecting surface may be, there is always the leakage of intensity happening when there is incidence of or reflection happening at a surface. Okay, again a very theoretical portion here, nothing else. Now, in what happens in total internal reflection? So, in total internal reflection, on the other hand, no transmission of light takes place, quite evident, because there is no refraction taking place. That means for this process the intensity remains intact or very near to intact. So, the angle of incidence, so this thing has been explained. Next is the angle of incidence corresponding to an angle of refraction 90 degrees, that means this portion here is say angle AO3N. So, angle AO3N, that means this angle has been talked about here, is called as critical angle, So, this angle IC is called as critical angle. For the given pair of media. Next is, so this thing has also been explained. Next is, we see from Snell's law that if the relative refractive index of the refracting medium is less than 1, then since the maximum value of sin r is unity, there is an upper limit to the value of sin I for which the law has to be satisfied, that is I is equal to IC, such that sin IC is equal to n to 1. Whatever they are saying is, I will try to mathematically compute it. So, we know that Snell's law of refraction says that sin I by sin r is equal to n to 1. Now, for this case scenario also, the maximum value of r which can obtain is unity. When it will obtain the value of unity? When r is equal to 90 degrees. So, let me just write that also. So, when r is equal to 90 degrees, sin r is equal to 1, and this is its maximum value which it can attain, maximum value. So, therefore, when we are putting r is equal to 90 degrees, we will get sin I is equal to n to 1. When r is 90 degrees, it is this sequence only. Therefore, we can say that at this portion I is equal to IC, and therefore, we can write that sin IC is equal to n to 1. So, from this thing what we can conclude, that critical angle can be directly find out if we know the refractive index of medium 2 with respect to medium 1. So, this is the only conclusion, this is the only explanation which has been talked in this last point. Let us move on. So, for values of I larger than IC, Snell's law of refraction cannot be satisfied. Why it cannot be satisfied? Because the angle of refraction cannot be greater than 90 degrees. If it is greater than 90 degrees, then the value of I will come as negative. Hence, no refraction is possible. The refractive index of the denser medium 1 with respect to rarer medium 2 will be sin n12 is equal to 1 by sin nc, quite evident, because we know that sin n12 is equal to 1 by n21, and n21 we have directly calculated right now, that which is equal to sin IC. Therefore, we will get n12 is equal to 1 by sin IC, which is written here. Okay, next is some typical critical angles are listed in the table. So, for medium of water, crown glass, dense flint glass and diamond, the refractive indexes are given. So, 1.33, 1.52, 1.62, 2.42. Therefore, when you will just do the sine inverse of them, you will get the critical angle equal to 48.75 degrees, 41.14 degrees, 37.31, 24.41. As you can see, therefore, glasses except water, everything has a critical angle which is less than 45 degrees. Let us move on. So, now all optical, so now there is a demonstration for the total internal reflection being done here. So, just try to understand this demonstration, so that you can understand what does optical fibers do, what are the applications, how can the application of total internal reflection can be done in our real life scenarios. So, a demonstration for total internal reflection. So, all optical phenomena can be demonstrated very easily with the use of a laser torch or a pointer, which is easily available nowadays. So, why do we use a laser torch or pointer? First of all, the ray of light is always at a straight line, it is very cheap, and next is that the demonstrations can be done in several colors. So, you can even find out where the color is going, and the beam of light is can be found at very small portions also. The diameter of those can be very small also. Okay. So, all optical phenomena can be demonstrated very easily with the use of a laser torch or pointer, which is easily available nowadays. Take a glass beaker with a clear water in it. So, let us suppose we are taking this scenario. So, take a glass beaker with a clear water in it, add a few drops of milk or any other suspension to water and stir. Why do we stir? So that water becomes a little turbid. So, turbid as in a little white, it becomes a little whitish. Okay. So, add a few drops of milk or any other suspension to water and stir, so that water becomes a little turbid. Take a laser pointer and shine its beam through the turbid water. So, now we are just taking a beam. So, we are just taking a beam and we are shining it. So, you will find that the path of the beam inside the water shines brightly. So, you can even see this, you can even see this. So, you find that the path of the beam inside the water shines brightly. Shine the beam from below the beaker such that it strikes at the upper water surface at the other end. So, it is trying to say some sort of this, to do this process here. So, shine the beam from below the beaker such that it strikes at the upper water surface at the other end. Do you find that it undergoes partial reflection, which is seen as a spot on the table below, and partial reflection which comes out in the air and is seen as a spot on the roof. So, what does it try to say? Let us suppose we are putting this beaker at a table. So, what is, and let us suppose this is the roof of this roof of the room in which the experiment has been talked about. So, if let us suppose this is that laser, so you can see a dot on this table, and similarly you can even see a dot at this roof also. So, what does it mean? It just simply means that there is a reflection happening also, there is a refraction happening also. This is reflection happening, this is refraction happening. Okay, fine. Next thing is now direct a laser beam from one side of the beaker such that it strikes the upper surface of water more obliquely. What does it try to say is, first of all, let us suppose we are starting, let us suppose this is the beaker. So, first of all we try to do it at some angle, then we try to increase this angle slowly. At one instance we will find a portion in which we will find nothing on the roof, we will find a dot only on the table only. That is the portion at which the total internal reflection has occurred. Okay. So, do you find, so this thing is done. Now, direct the laser beam from one side of the beaker such that it strikes the upper surface of the water more obliquely. So, this is being given in figure B now. Adjust the direction of the laser beam until you find the angle for which the refraction of the water surface is totally absent. What will be that angle? That will be the angle at which you can't find a spot on the roof, and the beam is totally reflected back to water. So, this is that scenario only this. This is total internal reflection at its simplest. So, this is the simplest explanation, this is the simplest way in which you can do the total internal reflection concept. Now, pour this water in a long test tube and shine the laser light from top. So, this is the explanation being talked about here as shown in figure C. Now, adjust the direction of the laser beam such that it is totally internally reflected every time it strikes the walls of the tube. This is similar to what happens in optical fiber. So, this is the scenario, this is the phenomena which is being explained or which is being done in which is the basic agenda of optical fibers. So, what does it try to say? Let us suppose this is your test tube, this is your complete test tube. Now, what does it try to say is, first of all, keep the angle and then just keep on changing the angle, just keep on changing the angle. You will find a sequence, you will find a portion at which there will be total internal reflection happening. Just put the stop there and you can find that the total internal reflection would be keep on happening. So, you will see dots at several locations on the test tube, and this is the similar thing which happens in a optical fiber also. Okay, so, that is the end of this portion also. Let us move on to two different applications of total internal reflection. The first is your prism, second is your optical fibers. So, please look over carefully, very important discussion, very important thing. So, first is your prism. So, what is a prism? Prism is nothing but an for a 2D diagram we can understand it as having a 90 degree angle and two 45 degree angles. So, basically it is an isosceles triangle. Okay. So, prisms designed to bend light by 90 degrees or by 180 degrees make use of total internal reflection. So, as you can see in this case scenario, it can bend the light by 90 degrees. So, what is happening inside you can't visit very with your naked eyes, but you can see that I incidented a light like this, it is coming like this. So, what does it say? That the bending of light has occurred at 90 degrees portion. Similarly, if I put the incidence like this and it is coming in this way, so as you can see a 180 degree rotation has happened or 180 degree bending has happened. So, this is one of the application of prism. Okay. So, prisms designed to bend light by 90 degrees or by 180 degrees make use of total internal reflection concept. So, how does it try? What does a prism do? So, the phenomena which prisms inculcates is nothing but total internal reflection. Okay. So, such a prism is also used to invert images without changing their size, for example in figure C portion. So, as you can see, even if the figure is not changed, you can see you can even invert the images. So, how is the inversion being done? As you can see, the image was like this in the first case scenario. After the after the light has been passed through the prism, as you can see, the image has been inverted. Okay. So, such a prism is also used to invert images without changing their size. In the first two cases, the critical angle IC for the material of the prism must be less than 45 degrees. Why it must be less than 45 degrees? Because as you can see that this is happening and this angle has to be less than 45 degrees to occur, because angle of I should be equal to angle R. For angle I equal to angle R, it has to be some sort of portion such that the value is occurring, or sorry critical angle is happening, because the critical angle, if it is greater than 45 degrees, it will not even occur in this surface. Okay, so also I explained you in the scenario when I was talking about this portion here in the table also, that as you can see that for these three glasses the angle of critical angle is less than 45 degrees. Okay, so next we see from the above table that it is true for both crown glass and dense flint glass. So, that was a table being explained. Next application is optical fibers. So, optical fibers nowadays optical fibers are extensively used for transmitting audio and video signals through long distances. Next is that optical fibers too make use of the phenomena of total internal reflection. So, how does it use this total internal reflection? So, basically optical fibers are fabricated with high quality composite glass or quartz fibers. So, these are one of the implications of optical total internal reflection. Each fiber consists of a core and a cladding. So, what is a core, what is a cladding? Basically this is the core and this is the cladding. The refractive index of the material of the core is higher than that of the cladding, quite evident, denser medium and rarer medium. So, this is happening here, and due to this total internal reflection occurs. So, now when a signal in the form of light is directed at one end of the fiber, let us say this is that signal being talked about here. So, when a signal in the form of light is directed at one end of the fiber at a suitable angle, so that is the suitable angle has to be such that at the inside portion of the optical fiber, the angle of incidence must be greater than critical angle. So, when this is happening, total internal reflection will occur. So, when a signal in the form of light is redirected at one end of the fiber at a suitable angle, it undergoes repeated total internal reflections along the length of the fiber and finally comes out at the other end. So, this is the angle at which it was incident initially, and this is how it emerges out. Okay. Since light undergoes total internal reflection at each stage, there is no appreciable loss in the intensity of light signal, which was the basic agenda of why we are using the total internal reflection concept. Optical fibers are fabricated such that the light reflected at one side of inner surface strikes the other at an angle larger than the critical angle, quite evident basic principle of total internal reflection. Even if the fiber is bent, light can easily travel along its length. Thus, an optical fiber can be used as an optical pipe also. Fine. A bundle of optical fibers can be put to several uses. So, what are these uses? Optical fibers are extensively used for transmitting and receiving electrical signals which are converted to light by suitable transducers. So, this basic concept which a basic of this will be explained to you when you will when the chapter of electrical signals will be explained, a communication system will be explained. Next is obviously optical fibers can also be used for transmission of optical signals. For example, these are used as light pipe to facilitate visual examination of internal organs like esophagus, stomach and intestine. So, basically a light pipe has been put through your mouth and that is being used for the visual inspection of your esophagus, stomach and intestine. So, this is the basic explanation of total internal reflection. First explanation was prism, second application was your optical fibers. So, let me stop it here only. I will move on with the further discussion in the next class. So, this was the basic explanation of your total internal reflection concepts. So, the course progress for you, we started with the introduction concept, then the second part, that is reflection of light by spherical mirrors, is also being done, refraction is also being completed. Right now we are on total internal reflection. After total internal reflection, we will go on with the fifth point, that is the deflection at spherical surface and by lenses. So, in this concept I will explain you what is lens maker's formula, what is lens equation, and so on. For each of these things you just need to remember, please strategize your complete studying of this lecture based on sign conventions only. If you know the sign conventions, 90% of the topic is done, rest part is just your application part, mathematical formulation and theory. So, let me stop it here only. Thank you so much.